Hi students, today we are going to have a insight about kinetically and thermodynamically controlled reaction. Now, what we mean by kinetically controlled reaction? For this, we are taking an example of a reaction, say where A is converted to two different products, B and C, via two different pathway, where the difference is in the rate constant. Now, in kinetically controlled reaction, the major product will be that one which is formed at a faster rate. That is, if here we are considering B to be the major product under this kinetically controlled state, then we can definitely say that K1 is greater than that of K2. For kinetically controlled reaction, basically we are considering delta G double dagger here. That means the stability of the transition state is considered for predicting the product of the reaction. Next, coming to thermodynamic and equilibrium controlled reaction. For such reactions, we will be considering the delta G0 factor. The product having delta G0 lesser will be the major product and vice versa. That means here, in contrast to the previous case, we will be considering the stability of the product. If the free energy of one of the product is less, we can say that will be the major product in the reaction. Next. Now here we are comparing and contrasting between kinetic control and the thermodynamic control. Here we are considering the same reaction. Now let us assume that for this particular general equation, B is the kinetically controlled product, that is KCP, and C is the thermodynamically controlled product, that is TCP. So obviously we have understood that since B is a kinetically controlled product, so obviously the relationship should be K1 is greater than K2. So for kinetically controlled one, we can also say that equilibrium constant of the reaction from A to C will be much greater than that of A to B. So if you substitute equilibrium constant in terms of the rates of the forward and the backward reaction, we will be getting the equation as shown, that is K2 divided by K minus 2 is greater than K1 divided by K minus 1, right? Next, this is the energy profile where we are seeing that, have a look, A is being converted to B and C via two different pathways. Since B we have considered to be the KCP, so it involves a transition state which is stabilized. That means it is having lower energy. And on the other hand, the one which involves the most stable product, that is TCP, will be passing through a transition state having higher energy, right? And where other symbols bear their usual meaning, right? Next, coming to the conditions, that is the conditions for kinetic control and thermodynamic control. If you compare, we will find that kinetically control means reactions occurring at lower temperature and taking shorter reaction time, while those of thermodynamic controlled reaction occurs at higher temperature and longer reaction time is necessary. Here we must remove one confusion, that low temperature and high temperature are very much relative term. It may vary from reaction to reaction. Okay. Next, this is the general example where we have added a halogen acid to a diene. Once the reaction is initiated by the addition of the electrophile, a carbocation will be generated. In first case, we are getting 2-degree allylic carbocation, which is definitely more stable compared to the another canonical form that we have written, that is equivalent to 1-degree allylic carbocation, right? That is obviously less stable as shown. Now, these two will individually get attacked by X minus, that is halide ion, giving respectively 1,2 product and 1,4 product. As we know that 1,4 addition product is more stable because it's more substituted double bond is present, so it will be considered as a thermodynamically controlled product, while the other as kinetically controlled product, right? Next, coming to specific examples, that is whatever we have taken in the previous slide. Here specifically we have added HBr, one at minus 80 degrees Celsius, another at 40 degrees Celsius. So we have already discussed, since minus 80 degrees Celsius is lower temperature, so obviously 1,2 product, that is the KCP1, will be the measure. And here also we find that the major product is the 1,2 addition product. And at 40 degree, 1,4 addition product is the major product. Now, if you hit the 1,2 addition product at higher temperature, obviously it will again equilibrate to give the more stable product. Coming to another example, here we are having substituted butadiene, addition of bromine. So first is the 1,2 addition and the second one is the 1,4 addition. But since in the first case, one of the double bonds is in conjugation with the aromatic ring, so it is obviously stable. So whether it is the lower temperature or at higher temperature, your 1,2 product is the major product. That is, both TCP and KCP is the same product, while 1,4 product is less stable. Clear? That means it is not always correct to say 1,4 addition product is more stable. Next, why we are getting KCP at lower temperature? Because KCP involves more stable carbocation, and hence the activation energy required will be less. Another reason behind is the proximity effect. What do you mean by the term proximity effect? That is, when the initial carbocation is being formed, before the delocalization can take place by the nucleophile to give kinetically controlled product, more at low temperature due to proximity effect. So what will happen? The nucleophile will remain as an intimate ion pair. Hence, the attack will be faster. Hence, we will get 1,2 addition product. Okay. Next. Coming to an interesting example where addition of alpha beta unsaturated carbonyl compounds are considered. Here we have taken an alpha beta unsaturated carbonyl here, and we are adding the same reagent, that is HCN and sodium cyanide. One at low temperature, that is 5 to 10 degrees Celsius, and at a higher temperature. Here the two products has been shown. One is the KCP, that is 1,2 addition product. Another is the TCP. Now, why we are getting such and such product, and why such product, that is TCP, is more stable? Here we find that at lower temperature, cyanide ion attacks the electrophilic carbonyl group, right, at a faster rate. The reaction is reversible and is kinetically controlled. But when you see that at higher temperature, the cyanide ion is specifically attacking the double bond. That means here a CC sigma bond is being formed at the cost of C double bond C pi bond. And obviously in the final product, C double bond O is retained. Okay. And we all know that C double bond O is more stable than C double bond C. Hence, 1,4 addition product is more stable. So since this TCP product involves a transition state having higher activation energy, so at higher temperature, when that activation energy is available, obviously we will get the most stable product, that is 1,4 addition product. Okay. These are the reference I have used. That is the book by Loudon, Claydon, and Shaha Pathak, and Study Guide to Organic Chemistry by Shah Chakraborty, Shahavasu. You can definitely follow these books. Okay. If you have any query, you are feel free to ask me. Thank you.